here's an example of the types of calculations you would do with titration data. Well, this isn't the most kind example, but I think we can do it. All right, so there's a lot going on here. An environmental chemist analyzed the effluent, which is a waste material, from an industrial process known to produce the compounds carbon tetrachloride and benzoic acid, which is a weak acid with one acid hydrogen atom per molecule. We'll get into that in a minute. A sample of this effluent weighing 0.3518 grams was shaken with water. The resulting solution required 10.59 milliliters of 0.1546 molar sodium hydroxide for neutralization. Yikes! Calculate the mass percent of benzoic acid in the original effluent sample. What on earth is happening? Okay, so let's draw a picture here. Let's see what's going on. So we would have our burette. Whoa, it's got the little valve on the bottom, the stopcock. It would have a flask underneath. Something like that. That's not a very good flask, but it'll work. Okay, so we've got to have a known solution and an unknown solution. And by known, we mean there's a solution of known concentration. And so if I look at the data, I do see that we know the concentration of the sodium hydroxide solution. It's kind of wacky, but we know it. So it's the sodium hydroxide that's going to go in the burette. So up in here is going to be my 0.1546 molar NaOH. That's in the burette. And eventually, I'm going to drip that sodium hydroxide solution into the flask. Well, what the heck's in the flask, right? Okay, so this waste product was a mixture of carbon tetrachloride and benzoic acid. But the carbon tetrachloride will not react with the sodium hydroxide, but the acid will. And eventually we're going to get a balanced equation that would look something like this. The acid from the waste mixture, HC7H5O2, it would react with the sodium hydroxide. And technically this is an acid-base reaction, but we'll talk a lot more about acids and bases later. For now, I see a double replacement where hydrogen is a +1 ion, and this big guy, C7H5O2, that's the -1 benzoate polyatomic ion. Acids usually contain hydrogen, so we could call this benzoic acid, or we could call it hydrogen benzoate. And then I've got sodium hydroxide, +1, -1. So acids often produce hydrogen, bases often produce hydroxide. So yeah, it's an acid-base reaction, but for now, let's look at this as a double replacement. And nowhere in here do I need to do like pH or anything that's real acid-base-like. It's just a reaction. Okay, so I'm going to switch the two positives or the two negatives. I usually just switch the positives because they come first. So I'd have sodium with the benzoate ion and hydrogen with hydroxide. Everything was +1, -1, +1, -1. So I know the products are written correctly, they're neutral, the whole thing is balanced, it's all +1, -1. HOH would also be known as water if that concerns you. And so really by getting the balanced equation, I'm going to eventually need to know the ratios, because this whole titration process is about mixing the solutions until we hit the stoichiometric ratio. Then we would stop. That would be our end point or our equivalence point. So I need to know that it's a 1-to-1 mole ratio. There. And that part in the description about the benzoic acid being a weak acid with one acid hydrogen per molecule, it just means that, like, there's more than one hydrogen in the benzoic acid molecule, but just the first hydrogen is the one that will react in solution. The C7H5O2, those 5 hydrogen are part of the benzoate ion, and so they are not going to separate in solution. Now, do you have to know all of this off the top of your head? No way. Now, for a reaction like this, we would probably just be given the balanced equation. Okay, so in a nutshell then, I know the concentration of the sodium hydroxide, and I want to know how much acid was in this mixture. And so in the bottom here, in my flask, technically in my flask is a mixture. This is going to be the solution with the carbon tetrachloride and the benzoic acid, the HC7H5O2. But the carbon tetrachloride does not react with the sodium hydroxide. So it's in here, but it's non-reactive, and it's not part of my balanced equation, and I'm really not going to study it. So in this mixture, this solution mixture that's in my flask, I want to know, like, what percent of that is the benzoic acid? What percent of it is benzoic acid? Interesting. I don't know. But now here's the concept, that I would mix these solutions, and so I would like drip, 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 drip. I'd be dripping in the sodium hydroxide until I hit the 1-to-1 molar ratio, which I would know because, I mean, even though they don't mention it, there would be some kind of an acid-base indicator also in the flask, so that the solution would change colors. And that's what we'll study later on when we really focus more on the acid-base component of this. Like, okay, what would be the pH when I hit the 1-to-1 ratio? What would the color change of my indicator be? For now, we're concerned with stoichiometry and just the general process that I'm going to mix these together until my indicator turns colors, and that will signal that I have reached the stoichiometric ratio in the balanced equation. Yikes! Where it's like, oh my gosh, like, what do I even do? Like, where do I start? Well, piece of cake. We start with the solution of known concentration, because I also know the volume needed for neutralizing the benzoic acid. This drip, drip, drip ended up bringing my volume down to 10.59 milliliters. So we added 10.59 milliliters of the sodium hydroxide solution. Okay, well, eventually I want to do stoichiometry so I can figure out how much acid was in that mixture. But do you kind of see where we're going here? That if I know it's a 1-to-1 mole ratio, if I can figure out moles of sodium hydroxide used, then I could use the ratio in the balanced equation to get moles of that unknown benzoic acid. Yes, I think I can do this. Okay, so you're always going to start your titration calculations with the solution of known molarity. So you're always going to know one concentration. And for that solution, you will also know the volume used. Right there, you have enough information to find moles of sodium hydroxide. So we take the 0.1546 molar sodium hydroxide. Molarity equals moles per liter. So I do have to change that volume into liters. I can do that. 0.01059 liters. Awesome. So I'm going to cross multiply. I guess I could leave 4 figures. They both technically have 4 sig figs. 0.00167 moles always where you start. There's got to be one solution where you can find moles. Now I can do the stoichiometry, solution stoichiometry. Just in that I had to use solution data, molarities and volumes to find moles, but then I can do stoichiometry. So I would then say, okay, 0.001637 moles of sodium hydroxide. Now let's do the stoichiometry. I don't want to know about the sodium hydroxide anymore. Let's get this puppy over to moles of that acid, HC7H5O2. Awesome. It's a 1-to-1 ratio, so right there that's super easy, right? Then I would have equal moles of the acid. Now, it doesn't have to be a 1-to-1 ratio, so I wrote it in there just for the process, that if it wasn't a 1-to-1 ratio, then I would need to take into consideration what the ratio was from the balanced equation. Okay, so now from here, there's lots of different routes we can go. And so I could just be done right here. I could say it's 0.001637 moles of acid. HC7H5O2. Okay, so sometimes we might be done. Maybe our final answer is just going to be how many moles of acid were in that mixture. Or we can take that a step further. So here they really want us to calculate the mass percent of benzoic acid in the original waste sample. The waste sample was this guy. It's this. 0.3518 grams of that effluent, which was this waste mixture that contained benzoic acid and carbon tetrachloride. But do you see what we could do now? Like, we could do a percent composition, but if we want percent by mass, I'm going to have to go one step farther. So I would want to take this guy, 0.001637 moles, and then just switch it to grams. C7H5O2. Well, I could do that. Cancel moles. On the bottom, I want it in grams. I want mass. So 1 mole would have the mass on my periodic table. I just have to add this all up. A hydrogen, 7 carbon, 5 more hydrogen, and 2 times the oxygen. I'm going to say 122.13 grams. So that when I multiply, I'm looking at about, oh brother, I guess if I'm really going to leave 4 sig figs, 0.1999 grams. Okay, so this was kind of an important number. This was kind of an important number. And so now we can do the percent part. Oh, okay. So I know it was about 0.2 grams of benzoic acid in the sample. The sample was 0.3518 grams. So if I, this guy out of the way, I just grab a blank sheet, now I can do the percentage. Percent benzoic acid in the mixture is the 0.1999 grams of benzoic acid, C7H5O2, divided by the overall mass of the waste mixture. There it is, 0.3518 grams of the, I'll say, waste mixture. And then we'd multiply it by 100 to get a percent. Oh, that's not bad, huh? I'd be looking at about 50 I'll say 56.83%. There. So I get that there's like a lot of vocab that kind of like the buret and the titrant and the analyte and the equivalence point and neutralization. But when you scale it down, as long as you kind of understand the procedure, the calculations are not meant to be crazy. It's just solution stoichiometry. It's just that I'm mixing two solutions until I hit the ratio from the balanced equation, which here is 1 to 1. There's always one solution that you can start with to find moles. You've got to have one solution that you can find moles of. Here it was our sodium hydroxide. We knew the molarity and we knew the volume delivered. And the idea is that after adding 10.59 milliliters, I would stop the titration because my indicator turned colors, telling me that I hit the 1-to-1 mole ratio from the balanced equation. So I can use those two to find moles of my known solution, and then I use the balanced equation to get moles of the unknown. It's like each step's not crazy. It's just presented in a different light. And now often then the most important thing is once I got right here. I had moles of that unknown acid. And from there, there's a bunch of different things you could do. Here they gave us moles. What if they told us that, I had 10 milliliters of the benzoic acid? What's the molarity of the benzoic acid? If you knew moles and they told you the volume used, you could say, oh, well, here's my moles, 0.001637 moles, divide by the volume used. You could be given volume. What if they said that this was an unknown acid and we didn't even know its identity, but we knew that it maybe reacted at a 1-to-1 ratio? Maybe they told me that it was a 1-to-1 mole ratio in the balanced equation. But I don't know the identity. But maybe I do know the mass. Well, could you find the molar mass then? Molar mass would be grams per mole. So if they told me, yeah, you had a 0.3 gram sample and it was just this acid, what's its molar mass? Oh yeah, molar mass would be grams per mole. So you could take the grams of the sample and then boom, you've got moles. Maybe they just want to know how many grams are in the sample. Then I could take moles and switch it to grams. I could stop there. Or we could do something like this, where we're looking for a percent by mass in a mixture. And so then as long as I know the mass of my, in this case, acid, and I know the mass of the overall mixture, I can find the percent by mass. So once you get here, there's all kinds of different things that you can do. Makes it a pretty fantastic little calculation that we'll for sure practice.